Welcome to the flipped recording for 2.08, Design of the Periodic Table. As we get started, don't forget about that science notebook. You do need to submit that as part 2 of your unit test at the end of the unit. So you do need a slide with notes and the guiding questions answered from each lesson. There are templates available for you that are already formatted with the questions and the lesson titles. So all the slides are together in one file. And those are found under Content in the course on the home page. So be sure you are completing a slide each time you complete a lesson. If you wait until the end of the unit to do the whole notebook at one time, it will take a very long time. So as we get started, if you struggle with note taking, as always, please listen for the parts of the lesson that I tell you to add to your notes page. And I'll also be covering the guiding questions, so be sure to jot down those answers. There are 10 guiding questions for this lesson, so a lot of content that is covered here. So we want to make sure we get all 10 of those answered. So as we jump into the lesson, remember I do encourage you to go into the lessons from the science homepage, go under Content, and then scroll down. Here you can see all of the things that you need to have completed. So as you scroll down to 2.8, anything that still has numbers, you still have lessons or things to complete in there. And then as you get into the lesson, I always include, if there's any information that's different or that you need to know, I always include that in the instructions at the beginning. So when you're working on labs or things like that, always look up here in the description. So in this case, there's not one, but up here at the top, you will see some instructions. So we jump into the introduction here, and we're talking about the design of the periodic table. So for thousands of years, scientists have investigated the way materials break down and combine with other materials. Eventually, they learned that some materials could not be broken down any further, and they called these materials elements. For some time, chemists tried to find a pattern in the properties for different elements. Then, in the 1800s, the periodic table was designed. It arranged the elements according to the pattern found in their properties. So that's an important thing to note, how the periodic table is set up. So in the early 1900s, however, it was discovered that the arrangement of the electrons in the atoms determines the periodic pattern of these elements. So they are arranged by properties, but most importantly, there's arranged by the arrangement of the electrons in the atoms. And we'll figure out a little bit more of that as we go. But guiding question number 1 says, how are elements arranged in the periodic table? So question 1 says the arrangement of their electrons determines their periodic pattern. So that is the answer to guiding question number 1. All right, as we move on to page 2, we're going to look at the lesson goals. It describes the design of the periodic table and explain how the elements are grouped into families and periods. We're going to interpret a diagram that displays information about a specific element, and we'll be able to identify the areas of the periodic table that group metals, nonmetals, and inert gases. And here are those guiding questions. So question number 1, how are elements arranged in the periodic table? And we'll see that answer again as we move into the lesson. So starting on page 1 out of 13, it says 200 years ago, scientists were especially fascinated by how the properties of elements seemed to repeat when the elements were listed in order of atomic mass. This repeating pattern was termed the periodic law. The arrangement of elements in the periodic table illustrates the periodic law. Dmitry Mendeleev, a Russian scientist, developed a periodic table close to the one we recognize today. Mendeleev launched the age of the modern periodic table and convincingly showed that elements follow the periodic law. So how does the periodic table proposed by Mendeleev differ from the current periodic table? So The table proposed by Mendeleev is organized by elements by increasing atomic mass based on the properties exhibited by the element. The modern periodic table is based on Moseley's work. It organizes the table by increasing atomic number. So if we answer that question again, number 1, how are elements arranged? It's not by electrons anymore. We're answering guiding question number 1. The elements are arranged by increasing atomic number. So that's your answer to guiding question 1. Question number 2, we're looking at how does the periodic table work, or why does the periodic table work? So here is a look of Mendeleev's periodic table. All right, so you can see it looks very different from what we recognize today, but it is set up with columns and rows. So why does this table work? Early chemists used the periodic table to predict how elements reacted with each other. However, they didn't fully understand why this arrangement worked. The answer was revealed when the atomic model was completed in the early 1900s. The atomic model showed electrons orbiting a nucleus of protons and neutrons. When the electron arrangement was discovered, the number of outermost or valence electrons followed the same pattern as the properties of the elements. So Mendeleev's periodic table showed the electron arrangement of atoms 28 years before electrons were discovered. So in a nutshell, the outer electrons of an element determine the properties of the element. So if you're looking at why it works, you can answer right in here, because the atomic model shows they are arranged, basically, if you're summarizing this, by the outermost or the valence electrons follow the same pattern as the property of the element. Okay, so if you are comparing the number of electrons the element has with the patterns of the property of those elements. Remember, properties are things that describe it, like its ability to burn or rust or color, smell, things like that. So those properties, along with the valence shell, outer shell electrons, match up, and that is how the periodic table, that's why it works in its arrangement. So pretty interesting that Mendeleev figured that out before they even had discovered electrons. So what are the outermost electrons called? And the outermost electrons of an atom are called valence electrons. So you may want to include that definition or that sentence in your notes as well. Those electrons reside in their valence shell of the electron cloud of the atom. That means they're on the outermost ring. And if you want to draw an image of that or something in your notes, that might help you remember it as well. And so guiding question number 3 says, what are the outermost electrons called? So you can answer that question as well, guiding question 3, and the answer is valence. So moving on, as you're talking about exploring the periodic table, we're looking for question number 4 on the periodic table. What are the groups and periods? So you know that rows of elements on the periodic table are called periods, and columns of elements are called groups. So question number 4, you can go ahead and answer that one with what are groups. Groups we know are the columns. They go up and down like columns on a house. So those are groups. And then periods are rows. They go across. And the way you can remember that is there's a period at the end of a sentence. So you can remember, you read left to right. That is a row. So that answers guiding question 4. Electrons are arranged in energy levels called shells. So if you look at question 5, it says, how are electrons arranged in shells? So we're answering that right now. Each shell has a maximum number of electrons it can hold. Electrons will first fill up the lowest energy shell. When that shell is full, a new shell begins to fill and is located slightly further from the nucleus. Each period further down on the table represents another added shell. So you can think about that. In hydrogen, being element number 1 at the top, only has 1 electron. As you work your way down, remember we're increasing our atomic number, we're increasing the number of protons, which also means you're increasing the number of electrons. And so you would have to have more shells because you have more electrons. So guiding question number 5, how are they arranged? So it talks a little bit about electron shell numbers, but you just fill each shell, and when that shell's full, you move to the next one. And then you may want to note that each period further down has another added shell. So if we look at the atoms over here for sulfur and oxygen, notice how sulfur possesses more energy shells than oxygen. So more shells are needed to accommodate those electrons. Okay, so you've got all of these for sulfur, and they have more. Oxygen just has 8. All right, so you can compare the difference there. So here it talks a little bit about those energy shells again. Take a look at the fluorine atom. So over here we're looking at the atom. You can see that there are 2 electron shells located outside the nucleus. So the first ring is always going to have 2. That's something you want to note. Also notice that the shell closest to the nucleus holds less electrons than the shell furthest from the nucleus. So the first ring is only going to have 2. And so that's because as you get further from the nucleus, there's more room to accommodate the electrons of the atom. So the atomic number of fluorine on the periodic table is 9, while the atomic mass is 18.99. You know this means that there are 9 protons and 10 neutrons in the nucleus. Because this is an electrically neutral fluorine atom, that also means there are 9 electrons distributed among the energy shells of the electron cloud. So how many electrons can you count in the picture of the fluorine atom? So you should be able to count 9. And how many electrons are in the outermost or valence shell? So if we know that 2 go here, there have to be 7 left. So 7 electrons in the outermost shell. So looking back at our guiding questions, let's make sure we're caught up. How are electrons arranged? We talked about that. They are added to their shells. And what are some electron trends within groups and periods? All right, so here we go. As you move across a period from left to right, elements exhibit 1 more electron on their outer or valence shells. So that's your answer to number 6. Okay. They're going to have 1 more electron than the one before. So look at these oxygen and lithium atoms. Oxygen has 6 valence electrons while lithium has 1. Moving down a group, the outer shell of the atoms in the same group all have the same number of valence electrons. Okay, so think about columns going up and down. They are all going to have the same number, and you may want to draw this out in your notes so that you can remember. Just draw kind of a makeshift periodic table, columns going up and down. They have an equal number of valence electrons, equal number of outer shell. But as you go across left to right, you're adding an electron each time. Okay? So the elements in the group have similar properties because they have the same number of valence shell electrons. So you can remember that groups are they're also called a family. And we know that while we don't look exactly like our family members, we have a lot of characteristics in common. So just like a family of elements, they have a lot of properties in common. And so it says, look at the oxygen and sulfur atoms. They're both in the same group on the periodic table, and they both have 6 valence electrons. So what is the trend in valence electrons for atoms within the same period? Okay, so talking about a period now, talking about going across. So what's the trend there? The number of electrons increase from as you go across from left to right. So that kind of answers that question number 6 as well. For a period, it increases from left to right, and then within the same group, they have the same number of valence electrons. So that answers number 6. As we move on, we have a little activity that just lets you kind of review everything you've learned about electrons right now. Electrons are very important to the arrangement of the periodic table. So check how well you can explain the terms associated with the electrons and the periodic table. So if you're watching this as a recording, you may want to pause, go match up these words, see how well you do, and then take a screenshot once you've got it all correct and put that in your notes. That's a great thing to have in there as well. So as we move on, we're talking now about electrons, whether they're shared or they're exchanged. And we're going to be looking at guiding question 7 here. It says, what happens when electrons are shared and what about when they are exchanged? So when elements combine to form compounds, chemical bonds form between the atoms. Bonds form when atoms share or exchange electrons in a way that gives each atom a complete outer or valent shell. So for example, most elements have 8 electrons to complete the outer shell. So that might be something to add to your notes as well. And if you drew that little diagram earlier with the model and the electrons, and you have the nucleus and then 2, so we know that builds up. 8 is a full outer shell. That's as many as it can have before it has to go on to the next one. So hydrogen and helium are exceptions to this rule, and that's because these elements only have 1 shell, and it can only hold 2. Remember, that first shell can only have 2 on it, so hydrogen and helium are not obviously going to have 8. So elements out of groups 1 and 17 are very reactive because they are just 1 electron away from a complete shell. So if you look at the interaction between sodium, which is in group 1, and chlorine out of group 17, we can see kind of what's going on here. So if you look at it here, sodium, remember, is Na, sodium chloride, which is table salt. Watch what is happening. So this has 1 outer shell electron, and we can count here 1, 2, 3, 4, 5, 6, 7. So this one wants to be full. So if we take a look, sodium loses that electron to become stable, and sodium now has a positive charge because it gave that away, and chlorine has a negative charge because it's taken on that extra electron. So that kind of gives you a little bit about how those elements bond. So still talking about bonding when they're shared or when they're exchanged. Let's make sure we got that question answered. When they're shared, a bond is formed and the element bonds together. So let's see. Making sure we have that answer. Highly reactive. Okay, I think we have it all. So what happens when electrons are shared? We have a bond, and then when they're exchanged, it's either giving one or taking one to fill that outer shell. Okay, so bonds form when they share or exchange electrons in a way that gives an atom a complete outer shell. So it's trying to get to 8. So that's the answer to number 7. So now we're looking at 8. What happens when elements obtain a complete valence shell? So looking here, elements are more stable when they obtain a complete valence shell of 8, which is an octet. So that would be your answer to number 8. And then you could probably add a little more information as we go. Elements in groups 1 through 14 will generally lose their outer valence electrons to return to the next lower energy level with a full valence energy shell. For instance, magnesium, which is in group 2, will lose its 2 valence electrons to obtain the full 8 in the next shell down. And when magnesium loses those electrons, it becomes a positive ion. So in this case, you get the ion Mg2+. So this is magnesium 2+, which describes the ion of magnesium. Elements in group 14 through 17 are going to gain electrons to complete their outer valence shell. So for instance, phosphorus, which is in group 15, will gain 3 valence electrons to obtain the full 8 in its valence shell. When a phosphorus atom gains electrons, it becomes a negative ion. So in this case, you get P3-, which is describing the ion of phosphorus, as you can see in those images. And so what happens when it obtains a complete shell, it is more stable. We know that. All right, the next question we're looking at, that answered number 8, it's talking specifically about elements in group 18. So group 18, it says elements in group 18 have what kind of valence shell? So they have a complete valence shell. That's the answer to number 9. Because of this, most elements in group 18 do not get involved in bonding. The first compound of an element from group 18 was not made until 60 years after this group was found in nature. Because elements in group 18 have a complete valence shell, they are relatively unreactive. And they also are known as inert elements. So I would definitely include that in your notes. Group 18 is special. They have a full valence shell already. They usually do not react with other elements, and they are known as inert elements. So make sure you write that down. And going from there, let's talk about argon. In group 18, it possesses a complete valence shell holding a total of 8 electrons, and that makes argon very stable and unreactive. Argon is used as a gas with a double and triple pane windows, and it acts as an excellent insulator. So interesting, if you have double pane windows, there's argon gas in there. And what effect, if any, will completing the valence shell for each of these have on the atom? So we've answered 9. We know that group 18, the shell is full, they're called inert gases, and they are usually unreactive. So here, if you complete the shell for bromine, bromine is in group 17, it just needs one more electron for a complete shell, and the atoms becomes negative Br1-, so bromine 1-. For sulfur, it is in group 16, so it needs a total of 6 valence electrons, requiring 2 more to complete its shell, so then it becomes a 2-. Rubidium, it's in group 1. It possesses only 1 valence electron, so it's easier to just lose the single rather than to try to gain 7. So it's going to give that 1 valence electron away to arrive at the next shell down, which already has 8. It's full, and that makes rubidium the Rb plus ion. Just the plus there indicates it's just 1. And then the helium atom. Helium is in group 18, and it contains a full valence shell. So even though helium does not have 8 valence electrons, remember, because it's special, it only has 2 electrons anyway. So, but that shell is full. So therefore, it will not form an ion, and it will remain just helium atom without gaining or losing any valence electrons. So we've covered everything for guiding question number 9 as well. And question number 10 says, what are general categories of the periodic table? So as we go on, here's a little practice activity. Again, talking about atoms sharing or exchanging electrons to form bonds. Atoms of some elements are more suited for certain other elements. So for instance, the groups 1 through 14, they lose electrons to get their complete valence shell, and we talked about 14 through 17 gaining electrons. So it would make sense that an element that loses electrons would work well with an element that gains electrons. And so this exchange of electrons is the bond that holds those 2 atoms together. So again, pause the video, go through these 8 questions, make sure you can get them all correct. If you don't get one correct, you may want to screenshot that or put it in your notes so you have that information later. So now we're talking about, really quickly, the last question, the general categories of the periodic table. So it's shown here. It's a very, very small picture. So again, you want to always make sure you have your color printout. I always recommend the ptable.com. but it holds here separate elements in the families according to their properties. So as you saw, properties are determined by the outermost electron. So what are the general categories of the periodic table? These include metals, nonmetals, metalloids, and noble gases. Metals tend to form bonds by giving up electrons to complete their valence shell. So metals are everything from 1 to 14. Okay, you do see some crossover here and with hydrogen over here being special. So these are all metals. And then the nonmetals tend to form bonds by gaining electrons. So that's 14 through 17. So this little section here are the nonmetals. Okay, notice that you have some crossover. And then you've got that last special, those inert gases, which is group 18. Those are also called noble gases. And they're very stable because remember their outer shell is full. So they rarely bond with any other element. Metalloids, which are kind of like this little zigzag line that run down, they have some properties of metal and some non-metal. So they have kind of a combination of things going on there. So make sure on your periodic table that you either have a color-coded version that break these down, 1 through 14, 14 through 17, there's kind of a mixture there, or right around 14, and then these noble gases. So how is oxygen categorized? It's a non-metal. What about calcium? Okay, calcium, we don't think of it as being a metal, but calcium is like in our orange juice, but it is classified as a metal. And then xenon. It's a noble gas, so it's over here in this row. So you can see the general categories: metal, non-metal, metalloid, and noble gas. So that's the answer to guiding question number 10. And this is a really cool little table that kind of sums up all of those things and gives you some more information, general info. So talking about metals, it shows where they are, it gives you some examples, and it also talks to you about properties of those. So this is a really cool chart that would be helpful to have in your notes as well. They are great conductors of electricity, they form bonds by losing electrons, and they form positive ions. So you might want to screenshot each of these categories here. So do metals, and then scroll down to non-metals. Make sure you click, get that information. Shows where they are, some examples, some properties. Noble gases, the same thing. Click on those, take a screenshot. And the same with metalloids, where they are, examples, and some properties. So this is a really good table with a lot of great information. So we've answered all the guiding questions. We've gone through every lesson in every slide page of the lesson. So now we want to go through, there's a lesson review, check over all of these things, and then there is a quiz to take. So once you go through these, you're able to answer all of these, put things in your notes that you may need a little extra help with, and then go take that 2.8 quiz. Remember, you can go back into the lesson and look up quiz answers. You can also use your notes. Usually there are only 2 attempts allowed on the quiz, so try not to guess. Try to go back and look up those answers. And as we wrap up, we've answered all of the guiding questions. So now just check for the flip follow-up session, our live session in Science for the Week. Make sure you come see me in Help Lab if you have any questions, and be sure to have a great day.